Colloquium. Our speaker today is Klaus Lehnertz, right?
Good.
Yeah, and as usual, let me introduce a little bit our speaker. So Klaus got his PhD in 1988 in physics in Bonn, but actually he had an interesting path before, because apparently before getting this PhD, he studied, of course, physics in Münster, but he also studied medicine, chemistry, math, and even philosophy. So definitely interdisciplinary. Then after that, he had a research fellow position in the Institute of Experimental Audiology in Münster, and then he was a research fellow at the Department of Epileptology in Bonn. And he's currently a professor of physics in Bonn. He's also the head of the neurophysics lab in the Department of Epileptology, and as well, he's the head of the Interdisciplinary Center for Complex System, and definitely he's interdisciplinary, so he's qualified for that center. Okay. And his research topics, let's say they are quite broad, and his interests are in medical physics, neurophysics, complex networks, and related stuff. And today's talk is going to be about critical transitions in the human brain, early warning signals, and prediction of epileptic seizures. Klaus, the floor is yours.
Thank you for the nice introduction. I was told to not show any strange things, nothing that has something to do with probably that you have never heard about, so I will probably skip formulas. I will just give you a brief introduction of this topic. What is this actually about, such that you get an idea about what kind of system we are talking about here, what critical transitions are in this system, and what can be done in order to control that, if it is controllable. We will see. Good. We talk about this system here. Everybody has seen that, everybody has it, and it is extremely complex. Some people would call it complicated. I would still call it complex because it is the strange interplay that we do not really understood between structure, function of all these different ingredients that produce some kind of emergent phenomena on every spatial scale. From the single cells, I don't say neuron because there are many other cells that we would also need to take into account, up to neuron pools, up to whatever, up to large brain regions. And this is the most important aspect here, we are talking about a nonlinear system, an open system, an adaptive system. Adaptive in the sense that it was designed to learn. Yeah? That means whatever we do with these system in terms of whatever we have learned in physics, we always do perturbation theory. And sometimes we do perturbations. It will learn it. Yeah? Otherwise you would not sit here. And I was not here. So this is the problem that we are faced with here, and of course, due to the openness, we need to take into account that there is many things that go into this system. Some kind of external fluctuations that go in, and as you know, and you experience this by yourself, if there are no external fluctuations, you produce your own. Good. How to treat that? Mathematically. Not that nice. So we have to find some way of describing that. It is, of course, a network. If you look at the connection structure that we have there, if you take all the length of all connections, is 2.5 times the distance between Moon and Earth. This is what you have in your head. Nice. And then, of course, this huge amount of functionings and also of dysfunctionings, and I will talk about dysfunctions today, that you would need to take into account in order to understand what is actually going on there. I mean, we are far away from understanding that, but at least we have some ideas of what can be done with this system. Oops, sorry. I will talk about one aspect of this dysfunction. This is epilepsy, which is probably the oldest disease known to mankind. This is interesting, and still, after how many? Something like more than 3,000 years, we have no idea what this is. Yeah? So we observe something, we have some good indications for that, we can do many things, but really understanding what is this is not known. This is something that affects roughly 1% of the world population. And I've written some people down here from which we either know from self-reports or from observations from others. You see, these are famous people that suffered probably from epilepsy or in some kind of a secondary way from other diseases and then were affected also by an epilepsy. The epilepsy itself is believed in many cases to be, not the epilepsy, but the phenomenon that you see here. This is a recording of the brain activity as an electroencephalogram. And you see here some kind of a transition into a seizure. And in many cases, the transition starts locally, somewhere in the brain, which is then believed to be the origin of this epileptic seizure. And there are also some cases where it looks apparently completely at the same time. The whole brain, or mostly the whole of the brain, is synchronized at the same time. Nobody knows exactly how this can work. There must be probably some kind of a pacemaker that says now all go into the same direction, but there is nothing known like that. What we see, or what is mostly the characteristics of this kind of disease, is the epileptic seizure. I have shown here some example. If we go a little bit further, what you then observe is that there is some kind of a transition from something that looks more or less irregular in terms of description of signals. You would characterize this as a 1/f noise, into something that is highly rhythmic, and then back. And that happens then recurrently. Yeah? If you look at the dynamics in between a seizure, that looks like a chirp function, something like singing birds. This is the reason why it's called brain chirps in some papers. And so the question is, what kind of mechanism is this that translates some dynamics that looks more or less random into something that is highly rhythmic, and then back? Yeah, so typically some mechanism that we can think about is then synchronization of what this workshop is or this school is about. This is a belief. Yeah, if this is really the case and what is actually the underlying physical mechanism for that, this is still unknown. Some aspects about this disease. As I said, this main characteristics is something like the occurrence of seizures. This is how epilepsy is actually defined. If you take an average over all epilepsies, and there are many different ways, and you find that on average the frequency is something like 3 seizures per month. But it could go up to 100 per day. Yeah? Mm-hmm. If you look at occurrences, it is mostly Poissonian distributed. So it looks like a random process. Could also be something else, but actually it looks like a random process, except for something like that when you have here some kind of local bumps. This is then seizures that are being related to some biological rhythms. Yeah, what you observed in women, ketamine epilepsies or something like that. Typically, these seizures are mostly for the subjects, not predictable. They have sometimes some feeling that something will happen, and this is then sometimes called the aura. But today we know already that the aura is already the beginning of the seizure. So this is some kind of a misconception, I would call it, because defining what is actually the beginning of the seizure and where does it end, if you only see the tip of an iceberg, you don't know when something will happen. Yeah?
I have a curiosity, because the aura sometimes appears without the seizure, am I right?
Yeah.
So the aura can or cannot be related
it
to
could also be something without a seizure.
Okay.
Yeah. So this is the problem. Yeah. If this was the beginning of something, and then there is some kind of a disruption, and then you experience this as an isolated event because nothing followed. Yeah. So there's some kind of causal relationship that you would expect in order to say this is some kind of a transition from to via the aura into the seizure. Yeah. But this is, as I said, this is hard to define. There's one exception on that. Oops. This is the so-called reflex epilepsies. Quite trivial. You look onto your watch and you get a seizure, reproducibly. Yeah? You can control it by looking like that. So you make the antagonistic movement and then there's nothing. The duration of this event is extremely short. It's roughly 1 to 2 minutes, except for something that is mostly not taken into account when you derive models for seizures, namely that the seizure can last longer. This is the so-called status epilepticus that can, depending on the extent, the expression of the status epilepticus lasts for months, and you don't realize that. People behave a little bit dizzy in that sense. No, could be for whatever reason. If it's a convulsive status, then you need to bring the patient out as soon as possible, otherwise they will probably die. No? So during the seizure, what you observe there is from 2. Yeah. Yeah. The problem is that this is mostly data coming from seizure diaries. Yeah, so this is self-reported. If you ask patients directly after the seizure, can you remember what was going on a few seconds before? They have amnesia for that. And interestingly, they miss roughly 50% of their seizures. They don't know about that. So the question, this is data from the early 90s, yeah? That was not known during the time that there is such a high uncertainty. Yeah? The question is, what do they lose? What? Yeah. So it is not clear. Yeah. This is, as I said, this is old data. It looks like as if it's Poissonian distributed, but we are not really sure how that really looks like. Otherwise, it would be nice to have a complete observation of the subjects, and then you could probably do something, and then also probably answer your question, but not with these data. Good. What is going on during a seizure? This is some kind of from 2, that could be some kind of an impaired mental functioning. And that was my seizure. That's it. Yeah? Up to you fall down and you lose consciousness. Something like that. Everything in between, depending on which brain regions are involved. And what is then interesting, that what is mostly seen from neurologists is the state after the seizure. And this is from either being completely recovered within seconds up to I am dizzy for the next week. Yeah? So this is extremely broad what you observe there. In between the seizures, people behave mostly normal. And you would need to have a good battery of tests to identify, is there some deficit, and if so, what kind of deficit is this? It depends on the brain region, it depends on where you are in the brain, what kind of functioning is being disturbed. Everything needs to be tested. And then, of course, then related to something that you would call normal. Yeah? There's some classification.
So they always fully recover. After the seizure, after a certain time, they always fully
recover. Yeah. So what I mentioned is already the main distinction between this generalized and this focal onset seizures, which is then what you can find in the definitions from the International League Against Epilepsy. So if you want to control that, this is just some slide that I've stolen from a colleague with the, sorry. From the beginning here, from the development of the first anti-epileptic drugs, for example, here with bromide, and then you're up to the early 2000s, where different kinds of chemicals, okay, go ahead.
Is it known what other animals have these kinds of epileptic seizures?
Dogs, cats, I'm not sure about monkeys.
No, it's quite common actually. You see seizures in a large number of species. It gets more difficult, that's still because of biology
It's the same behavior for all
Yeah.
species.
Yeah.
Rodents are used for experimental purposes, and people are used primarily.
It's a nice question. The question is why? Why do they have that? Why do they have that over a complete range of organizational structures? Yeah? Not clear. So, control. If you see here, this is just over the last 20 years, there was an explosion of different systems and methods and techniques developed in order to control seizures. Controlling the seizures, not epilepsy. Yeah? So whenever you do something, you try to minimize the impact of the seizures, means you reduce the seizure frequency, but you probably will never treat epilepsy as a whole. No? And despite all what we have here, this is everything that is allowed to do. This is mostly any kind of neurochemicals that are either agonistic or antagonistic to some neuronal functioning or also glia functioning, combinations of that up to some kind of an active control with electromagnetic fields, with whatever is even cooling down would be some kind of a way to approach some kind of control. Still, roughly 1/5 of these patients, there is nothing that can help. Yeah? So and these are probably then the candidates that will then go into another kind of an approach. I mentioned the first one. This is the drug treatment. You see this, the effect, or the effectiveness is roughly 70%. That means in 70% of these cases, you can reduce the amount of seizures such that the individuum would say, I can live with that. Yeah? Not more. Surgery is one technique that is used in order, only in cases where the other treatment options will not work anymore, and you would need to identify a brain region on which you can operate on. Yeah? And then if you look at
So in a person is always the same region? In a given person is always the same region where it happens, or not?
Hopefully.
Okay, but before doing the surgery, it's better to know, right?
This is exactly the task. Yeah?
Okay,
If you can identify exactly that one and only that one brain region, then yes. Otherwise, I mean, if you put it onto the top, remove the brain, and then you are free. Yeah? But this is not what we want. Now, there are, of course, cases where you have multifocal onsets. And in that cases, the question is there something that leads and the rest is some kind of a secondary phenomenon, or what is this actually? Yeah? If you look at the success rate there, this is the average, is 60%. Yeah? But that ranges from 2. The epilepsy surgery is now quite old. This is a well-established technique. This is much improvement there, up to robotic systems that do that for you. Microsurgery, whatever can be done on that case, but it is surgery. Yeah? That would mean you set a scar in the tissue. And if you wait long enough, you have modified a structure. So it is not to wonder that this type of dynamics will come back. And this is exactly what we now see after roughly 50 years of experience. Yeah? So depending on when you do what, that might be an option, but in many cases this is not an option. So then there is this new version, which is then called neuromodulation, where people try to interfere with the brain in many, many different ways. But here the idea is ranging from I try to disrupt the seizure up to I try to modulate the brain dynamics in a way such that the seizure will not occur. This is, of course, then a long-range process, because what you need to do is then some kind of an relearning of something or de-learning of something. And if I ask you, how can you de-learn toothbrushing within the next week? You probably will not be able to do that. Maybe also not for the rest of your life, unless there is some kind of control that makes you do that. So any other, we have no idea about what is the long-term outcome of that. Yeah, this is too new. This is something that has been developed over the last 10, 15 years. So there is kind of a little bit of an experience, but not that much. And there's then, of course, the idea of some kind of a behavioral intervention or self-management. Let them do it on their own. They know how to do that. Yeah? Something like that. But even this is not clear because this is rare and nobody knows how this actually works. The reasons for all that is that there are many, many, many unsolved issues, particularly if we speak about epilepsy in humans. We have, of course, many, many findings from animal research where specific animals are being modified in a way that they mimic something like epilepsy. It looks like epilepsy, but if they really have epilepsy, particularly then in rats or in mice, how do you test that? Yeah. So the question here, the basic mechanism, how does this look like in humans? If you find something in the rat, how can you translate it to humans? Is this translatable? Up to some sense, maybe yes, but not in general. And then, of course, what is where and when and why and how in the brain do seizures start? Particularly the why. This where can be easily identified in many cases. How this then starts, this is also some kind of debatable issue, which is also this workshop on, or this school on. Is there something like a precursor for that? How does it spread? Yeah, you asked, is this always the same? It's not always the same. Right? If you take the same seizures in the same subject, the spreading might be in that way, in that way. It could be local. There could be a spreading even to the opposite brain hemisphere. This is not something that is consistent. So it's highly, highly, highly variable. Why do seizures end? Energy depletion? It is not that. It is probably a synchronization mechanism that leads to the end of the seizure. I will show you some examples for that later on. Yeah, but this is highly unintuitive. What is going on during the interval between seizures? Is this really some kind of a normal behavior, just from the observation, just from interactions with other normals? And then they say, that is normal. Is there something that is pathological? And of course, what is going on then, because it is in the same system. Yeah? You have this normally functioning brain up to some events where there is some kind of a dysfunction in the same system. So some kind of a coexistence of different types of dynamics in the same system. How to test that? You see, this is quite complicated. Yeah? We have basically not much knowledge about the long-term dynamics, really long-term. I mean, this is something from observations that we have, either taking some samples only from the seizures or some kind of observations over maybe longer years during, longer times, not years, during some evaluation phases, but that's it. Yeah? And then, of course, then the conceptual side for the clinicians, a concept like this, the epileptic focus, this is, of course, highly attractive because in terms of surgery, there, yeah, and not there, yeah, that makes sense. But it is a network phenomenon. Yeah, of course, the brain is a network. So there is some kind of an alteration, a functional alteration, or the structural alteration, or both, in the same system. How can we assess that? There are lots of techniques to do that. Now, if we start from the macroscopic level, also non-invasively, we can measure the EEG or also the magnetic counterpart, the magnetoencephalogram, with different methodologies. From very simple sensors, as it's shown here, where you place some electrodes on the head, up to superconducting quantum devices. Yeah, nice, works. Yeah, and the new versions that we have, they can even walk around with that. You don't need some kind of a cryostat on your head to run around with that. So maybe then on the the more local level, and this is something where you have access to only in these cases, you can implant electrodes either onto the surface of the brain or into deeper brain structures. And if you then go to the more experimental side, if you're measuring single unit activities or even multi-unit activities with specific probes that are brought into the brain, and then you have access to single neurons. Take into account you only can manipulate it from outside. You need to hear that if you have measured something. Yeah? Hitten mentioned the next generation probes where you have combinations also with neurochemistry and temperature measurements. this is a little bit of the future, but within a couple of years, we will probably have then much, much more multimodal information than what is currently available. So if you look at what you have on brain dynamics, I mentioned it already before, it depends on the timescales that you are looking at. What you mostly find is something that looks 1/f-like. Then you have the impression this is noise. If you zoom in and you zoom in and you zoom in, you have the impression that this is scale-free. And what most people do is not analyzing this so-called background activity, but because there are some nested oscillations on top that have well-defined frequency bands, and then you have patterns, and this is then what you can easily identify also by looking at the EEG. Yeah? This is just one aspect that you have here, is that you have effectively no structure where you can look at. Structure in the temporal domain. If you go to the spatial domain, you have, of course, then the problem that whenever you go to the single unit recordings down here, you have spikings. If you go for local field potentials, if you take groups of neurons, you have then some kind of a superposition of all of them. And if you then go to the macroscopic activities, you have something, then there is nothing like relationship to spikes. Sometimes you can find some relationships that something is successing here or it's starting here, but on average, there is not a big relationship where you can say spiking up here makes some kind of wave-like behavior on the macroscopic level. Yeah? From the observations that we have. There might be something else, but this is so far the data that is available. Good. There's a lot of history in trying to interpret what can be done on that side, and if you go back into the literature on EEG analysis, you will find whenever there was some kind of a novel development in physics, mathematics, whatever, in fact, basically the first signal that was analyzed was that in the real world system is the EEG. Yeah. Early applications of the Fourier transform, of whatever has been done so far, this is mostly data from EEG. And if there was something like data that is available or findings that would make sense also in interpreting the brain dynamics of an epilepsy patient, there would have been some success so far. Yeah? But there were roughly 50 years where there was nothing. Interestingly, with the advent of the nonlinear dynamics and particularly the development of the nonlinear time series analysis technique, so any kind of estimates of dimensions of Lyapunov exponents, entropies, whatever was there, has of course been tested. Yeah? And the funny thing was that also with these methodologies that you had here, there were also first observations where you could see that prior to seizure, there is something going on. In specific regions of the brain, it looks like as if the brain gets less complex. It reduces its the dimensionality of the dynamics. Lyapunov exponents move into the direction of being more chaotic, if you interpret it like that. Yeah? So the interpretation from the side of nonlinear dynamics, the translation to neurophysiology again, this was and is still critical, how to do that. Yeah? So there had been many, many ways and using these techniques where there was an improvement of many of these pre-surgical evaluation techniques in terms of how well can we localize something, can we lateralize the brain regions, what is the impact of anti-epileptic drugs, what is the impact on cognition. I don't want to go into these details, this is 25 years of research. Yeah? But there was something. The next was then, I skipped that one here, this is just one example. The next one was then since the 90s, there was also then the development of methods to understand interactions. Measuring interactions is not easy, particularly when you cannot perturb the system, because you don't want to perturb it, so you can only measure aspects of an interaction from observations. That means you would like to know how strong is an interaction, is there probably some kind of a direction, And ultimately, you would also like to have some ideas about how would the functional form of that would look like. A huge methodology, a huge battery of techniques ranging from statistical methods up to phase relationships, over entropy relationships, up to interacting stochastic systems, where people use the Kramers-Royal expansion to measure interactions between drift, diffusion, higher order terms, something like that. Yeah? Just in order to improve on the whole methodology. And in that case, it was quite interesting to see that if you measure these interactions, and the whole theories that were available during that time, that the seizure is nothing else but it is some kind of an onset of a building up of a critical mass in terms of their brain gets more synchronized. It is not like that. What we effectively see is that there's a desynchronization prior to a seizure. That is unintuitive. Yeah? It is not unintuitive if you think in terms of a network. If you say, I have some structures that need to build up this seizure activity, and in order to build this up, they need to get into some kind of an idle state. Leave me alone. I am the trigger. I will do that now for you, and then we can go together. Yeah? This is a completely alternative view. And here's another example for seizure ending. It's shown down here. What you here see, this is the eigenvalue spectrum of the correlation matrix in the moving window fashion. And what you see is that during the seizure, the largest eigenvalues, they are much, much smaller than the bulk. But close to the end, there is a re-increase. That means that the brain synchronizes in order to stop. This is not just a single case. This is data from more than 100 subjects, more than 200 seizures, including also the seizures where you have a status epilepticus and so on and so on. Yeah? So if you find something like that, how would you claim or how would you describe spreading phenomena? Yeah? What the clinicians typically do is they try to identify the very beginning of the onset of the seizure. That means here you have some kind of a transformation of this background activity. Sometimes you have also some spiking behavior there. But if you go and then if you have the electrodes in the right place, you will then see that there is here some kind of a transition into something rhythmic. Yeah? And then later on, it's in these channels here. Describing that and what are actually the mechanisms.
So each line is one electrode.
Each line is one electrode.
And this is the time direction.
This is the time. It's down here. 1 second, and this is the amplitude. Yeah? The spreading patterns that you observe, how does this spread? What kind of spreading mechanisms are behind that? This is largely unknown. People are currently working on that to find, is there some kind of a unified description or unifiable description for spreading patterns during the seizure? Also, in order to understand which brain regions are involved later on, will there be some kind of a secondary generalization such that the patient will probably fall down or it goes into some risky situation? The case is here that it is this misbalance between wordings. Yeah? What you hear or what you can read in the literature is that seizure is synchrony. Synchrony in the sense that you have something that looks rhythmic. You have a transformation that comes from something that is more or less irregular to something that is rhythmic, so there must be some, you describe this as synchrony. This is not synchronization. This is not this active mechanism. Yeah? And this is also something that you can then see that if you use different types of different methodologies in order to describe that, you will find either you have something like local phenomena in space, but this is really like spots, or you have something, depending on how you look at that, in terms of phase synchronization. If you look at the time matrix there, you see here some kind of bursts that pop up, and that's it. Depending on how you look at that. Yeah? And if you then take data from either from human recordings or even from animals, this is some kind of a large battery of different techniques. And if you look at what is the way how you characterize this, is this a phase relationship? Is this amplitude relationship? You can do this much more in a much broader sense and ask, are phase spaces comparable? Yeah? Then you will find that you either have an increase or sometimes you also have a decrease in synchronization. So what is this then? Yeah? You need to take into account that this is then also then in relation to the spreading phenomenon. And here's this now the enlarged view of what I have shown you before. The correlation matrix. Oh, shit. The correlation. No. Sorry, the correlation matrix in a large format here. You see it already here on the EEG. If you look at different cases here, you see that at the end, it is a much broader phenomenon. Traces look more similar than before. And if you then compare largest and smallest eigenvalues of the matrix, then you see that there is some kind of, if you hear with the normalized seizure time, everything is normalized because of the high variability of the seizures. Seizure duration that prior to the onset, prior to the offset of the seizure, and this can be easily defined. Yeah? You see that there is some kind of a re-increase, and that leads then to the claim that it is probably a synchronization mechanism that lets seizures stop, which is counterintuitive, but it makes somehow sense. Yeah? You have probably some kind of a phenomenon that would run until infinity, if there was nothing that can stop it. And if it's not energy depletion, then there must be something else. And here's an example for this status. Yeah.
To the previous slide, if you could explain what that figure is better.
This one
I'm
here.
not sure I fully understand
Yeah.
it. Yet.
This is the cross-correlation matrix at zero lag from all channels. But what is shown here is now the eigenvalue spectrum ordered from the largest to the smallest one, in relation to what you have before. And then you see that during the seizure, the largest eigenvalues that are still up here, they are decreasing. And all the information is contained in the bulk. And this is something that you would never look at. All the different techniques that do dimension reduction, PCA, Cahoon-Loewe decomposition, whatever you're doing, yeah, they only rely here on the very first trace. And this is probably the mechanism that they see, that there is some kind of a decrease. Yeah? But they would never look at this information here. Only at the end, you see that the largest ones get back, and that is then the mechanism that lets it stop. If you do the same for a status epilepticus, take into account this is now a seizure that lasts 4.5 hours. Yeah? I'm happy to have that data. This is the only single case that we have in our department. That is extremely rare. And here you see that there's an onset of the seizure and it tries to get back, it doesn't work. And then in between there are many ways where people or the clinicians try to stop that, giving drugs, doing this, doing that, and never succeeded with that. And then only here at the end, you see that the spectrum here, the eigenvalue spectrum gets much stronger here, and then the seizure ceases out. This was before we set up the first conference on seizure prediction. It was just a wrap-up of what is currently available from the different methodologies, from different observations. What can be extracted from observations? Is there something like a precursor? Yeah? So the red line that you see here is the clinically defined onset of a seizure on the EEG, not any kind of clinical movements, but there is a change on the EEG that clinicians would then identify as seizure onset. You see, this is roughly everything here in the order of a couple of minutes, taking into account that there is an uncertainty, which is roughly here that line, which is uncertainty in defining seizure onset. If you go to different clinics, if you go to different schools, how would you define that? How would you define that? This is uncertain. Many ways of doing either linear techniques, which is around here, looking at the autonomous system, heartbeat, you measuring energies with SPECT and PET techniques in order to estimate what is the energy consumption of the brain, asking subjects if there is some kind of premonitory symptoms. And you see that this group here of nonlinear techniques, that they showed on average there's something going on in the order of 5 to 10 minutes. If you go for interaction measurements, you can extend that up to hours. This is what is going on here, and in that way, people showed that there is much more. These are single observations, single data, your own data measured in your own lab. The question was then, can we extend on that and make it better? And this is stolen from our most recent review on this field, the whole development. So it started somewhere here already in the 70s, where people had the idea to look at, is there some kind of precursors up to when we have written this report. So there was a setup of an international research group to see, is there kind of evidence for epileptic seizures. They meet regularly. We shared databases, we had conferences on that, we made contests just in order to improve on the whole situation. Can we do better? Why is shown here? Instead of giving anti-epileptic drugs, you would need to take it for the rest of your life. Yeah? Is there a way to have something like an on-demand treatment? Yeah? If you only try to treat the seizure, but not the disease behind that, because you cannot really define it. Yeah? That would be some kind of an idea like that here. You have some implantable device or some device that measures something, some kind of activity, some kind of intelligence that runs some calculations, whatever is the best case. And then you have then many options, either warn the subject, there will be a seizure, do something, or you have some kind of a fast-acting pump that brings something into the body, or you do any other kinds of on-demand control schemes, like, for example, local cooling, yeah? Or electrical stimulation, or local drug administration, or whatever. These are systems that are already in use in other types of diseases. They have been developed in epilepsy research, interestingly, but they were never got into use there. And the reason for that is probably that the success rate is too low so far. And the question is, why is that? And if you go to the, basically the latest development, that was a development from the NeuroVista company in the US. They did, together with a group in Australia, did a feasibility study. Yeah? So knowing that whenever we have such a device and you bring this into the brain, and I tell you, you will have a seizure now, nothing will happen, because I have perturbed your brain in such a way that irrespective of what's going on, nothing will happen. Yeah? So that was just, you have some device that you bring into some measurement device that you bring into the brain, you have some kind of a control system, and then you have some connection to some system that gives you only the information, like flashing light. If it's green, you are safe. It's yellowish, do something. It's not red. Yeah? Red would then really mean we do predictions. Internally, there was something. Yeah? So that was observations from up to 3 years of continuous recordings in some subjects. And the funny thing was here, prediction is feasible, but not in all subjects, not in all seizures, not in all seizures of the same subjects. Good. For development of a device, this is probably sufficient. For researchers, you ask, why is that? Why is this not feasible all the time? What is behind that? We have this data, and we really don't understand what is going on. So you need to ask what is different in this sense. And if you go back and look at, for example, the measurement device that is here, you place some electrodes onto a brain region of which you assume that this is the onset, the area for which you observe the onset of the seizure. Not knowing if this is true. Yeah? If you look for seizure precursors, where are they being generated in the brain, then you will find that it's mostly not there. Yeah? And there are many, many techniques, analysis techniques, that now show that if you take into account the whole information that you get from the brain, from these subjects, then you will mostly find seizure precursors in other brain regions that are far off the assumed or presumed or even identified epileptic focus. So, another structure in the brain is responsible for something that is later on being seen in a specific region. What is this? Yeah? The other problem is, if it's mostly far off, you would need, if you go into some kind of a causal relationship and say, okay, if this was then the generator, we need to perturb there. Yeah? But this is mostly in brain tissue where there's nothing. This is the normal functioning that generates the seizures. Some deviation from the normal functioning, but not at this position. So in that sense, we would need to have some kind of a device that monitors as much as possible. This is, of course, something that is not available right now. That has led to a complete redefinition of the whole concept also on the clinical side, namely we go away from the traditional concept of an epileptic focus to something which is then called the epileptic network. That makes sense, yeah? But that would indicate that any brain region can generate seizures, which is, from the treatment side, kind of spooky. Then you would need to control the whole brain and not something that is designed to be locally. And all the devices that I have shown you before, they are extremely local. Yeah? I forgot to say the challenge here is, of course, that this network is not stable. It's a time-evolving network. And this is what it makes it much, much more complicated. So the question is, if we do this paradigm shift, we end up with an inverse problem. Namely, we would need to define what is an edge and what is a node. What people typically do is you define a network that you have access to. So you take your sensors that you have placed, that could be electrodes, that could be some kind of coils, that could be voxels in an MRI system, whatever you are doing, and you associate that with the nodes. And then, if you ask what is then an edge, we don't have access to the true edges, to the cabling in the brain. So what we do is we resort to some functioning and say, if we observe a similar functioning at two different nodes, similar in the sense that it is not some kind of a stupid statistical relationship, but there must be some kind of similarity in terms of the phases might be the same, the amplitude might be the same, any kind of characteristics that you derive from observations would allow you to say this is an edge, a functional edge. There's a relationship between these two, some dependency. And then, if you have that, then you can set up these networks, and then you have the whole field of graph theory available to characterize these networks. And this is the current ongoing field where people try to understand what do we learn about these networks using graph theoretical concepts, together with concepts from nonlinear dynamics, together with concepts from complex system theory, to improve on that. Yeah? This is state of the art. I can show you some examples on that, but here are some previous observations. We can identify that the epileptic brain networks, that they differ from normal ones, irrespectively depending on what you are doing. Yeah, that could be either in some awake state or some sleepy state or whatever. There is a difference. We can modify these networks also in the temporal sense by some cognition. This is also quite interesting, also in terms of control, not just doing something that is extremely local, but what will happen if we can think of something. It's also some kind of control scheme. Yeah? Use your brain. Many other aspects here also in terms of controllability of seizures. If you know that the networks during the seizures become more assortative, No chance. And this is also something that is seen in many of these control schemes. The further you go into the seizure, the harder it becomes to control that. You can do it on the beginning, but not later on. Leave me alone, I do it now. Yeah? This is the message that is behind that. I showed you the synchronization mechanisms. What is interesting here, sorry for that. If you use concepts from graph theory and you ask, for example, with centrality, does that what clinicians define, is this the same as we can see? Is this an important node or is there an important edge? If you pinpoint this down to the level of network ingredients, then you will find it is not, it is never like that. Yeah? So this is also this support for this paradigm change that there is something else going on, except for I do some kind of a local observation, then I say it is there. It is not like that. And for the long-term dynamics, this is of course something that needs to be studied much longer, because there are also very strong influences from driving structures like the moon and the sun and whatever we are doing during our daily life activities. Just one example here, what we observe in the pre-seizure state, that there is some kind of a formation of bottlenecks. And this bottleneck formation is not in this brain region where you expect it to be there, namely there where you can see the seizures, but that happens in other brain regions that are not affected from the disease, obviously not affected, but on time scales of hours, and then only when it comes to the onset of the seizure, then there are much more involvement of other brain regions. I don't go into that details here, what we have on the right, because these are based on different concepts of centrality. If you have that, we have these observations here, that we have lots of doesn't work anymore, lots of indications that there is something like a pre-seizure state. We have all these therapies, more than 30, but still the success rate remains at 50%. Is this chance level? And the question is, why is that? Yeah? And then you need to think about what is actually going on. If you look at all these different types of devices that we currently have, they work on their own. They are, of course, not related to any kind of detectors where you say, I have a pre-seizure state. The current detectors work if there is some kind of a little bit of higher activity, some kind of threshold crossing, and then they do something. But that's it. So there is no connection to some kind of precursors, and most of these devices, they target the clinically defined epileptic focus. They are not yet designed for a network concept. Another aspect, if we want to understand the transition to a seizure, we would need to ask what is going on in that brain. You would intuitively assume that you lose probably something like stability. You can also go for other concepts and relate this to resilience. Yeah? Resilience in a sense, like in engineering resilience, you go into some undesired state, but you have the capability to go back. Yeah? Could be also some kind of a multi-stability landscape where you hop in between different local regimes where you find something. So this is nicely presented here with this thing here. There had been claims about that could be some relationship to critical slowing down, but this is still debatable if this is really critical slowing down, what we see there, or if there are other mechanisms. And other mechanisms, this is shown here, that if you estimate resilience from interactions between the different between all different brain regions, and you ask for how stable are these interactions over time, and you do and end up with some kind of clustering schemes where you then try to estimate how resilient is the brain actually, and you see here on time scales of days that resilience increases prior to seizures. Again, an indication for leave me alone. Yeah? I don't want to be controlled. That could be a message like that. Yeah? And of course, you would need to take into account that all these deviations or all these fluctuations that we see there fluctuate on even much, much longer time scales that come from biological rhythms. Something that was not taken into account, also availability of data, recording during, when does it start, where we have something like continuous recordings. This is parallel to computing power, storage capacities, cheap storage capacities, because that generates lots of data. So availability of going into that direction, this is only recently where people can look at that. Few words on modeling, and then I'm done. There are, of course, people that try to understand that on, not from the observation side, but can we derive some models where we can do something with that? And what is interesting to see that in many cases, depending on the scale that you use, so either from a single cell, be it a neuron or whatever, up to networks, up to the global system, there's tons of ideas available. Yeah, be it some kind of ODEs or coupled ODEs or whatever. Yeah, even on the other side, you say, I do this with some kind of stochastic approaches. Everything is available so far. What you find in that cases here is, particularly if you go for networks, that these are mostly then related to some regular structures, which is, of course, not something that you observe in the brain. Yeah, if you ask neuroanatomists, what kind of topology has the brain? I say something in between. In between what? Yeah, that looks like a scale-free network which has nested small worlds. It looks like. We don't even have names for that. Graph theory has no names for that. So how to characterize that? This is then the next problem that we are faced with then. These kind of approaches, they study the dynamics, not taking into account that there might be some connection structure behind it that also produces something. Yeah? And if you look at the data that is being generated with these kind of models, these models are able to seize. Yeah? This is, I don't know what, this is your simulated signals, these are the real signals, and this is simulated. If you look at the comparison, this is striking. Yeah? It is almost perfect. It is almost too perfect. Yeah? What you have there is some kind of a description of specific aspect of specific types of dynamics. But that's it. Yeah? This is the only way that can be achieved with that. You can also build some kind of a transitions to that. You can also model a little bit of the spread. But if you then ask, is there something like self-termination? Or what would you need to do with these models such that these kind of activities stop? Then it becomes unphysiological. Yeah? And I mean, whatever you have here, if you look at these phenomena that are being used, ODEs, what kind of solution do they have? Something that oscillates. That's it. Yeah, it is to be expected that you will find something. Then the question is this a good model? There's more. If you take into account that the coupling structures that we have in the brain, or the structural organization is not a lattice, and it's also not a random network. Is there something in between? And in between that was, of course, the idea that when Watts and Strogatz came up with the idea of how to generate small worlds, people also now, of course, looked at that. What will happen if, let's assume we have a small world. What will happen then? No analytic solution anymore. We can only do numerics with that. Yeah? Still, what you find is that you can mimic transitions into the brain, and into the seizure, and out of the seizure by modifying the coupling topology. The dynamics is always the same. You only modify the coupling topology, and you can generate something that looks like seizures. We did the same also with very simple networks, where we observed also these phenomena here that we see a decrease in synchronization prior to seizure with very simple two interacting networks of integrate fire neurons. You balance a little bit the excitation-inhibition relationship, but you would need to have the small world topology in order to see that. Then you can mimic many other things. And I'll show you some examples here. On the upper left, this is an 500 by 500 integrate fire neuron network on a small world topology with where the integrated fire dynamics has also included some delays in order to mimic realistic synapses, but we only consider the pulses. We are not interested in it. I know it goes up and down. I don't need that. I only would like to have the pulse. And what you see there in black and white is the firing of the single neurons. And if you look at the network, this is now a network, a small world on a torus projected back onto a lattice. You see that you just let it run, and it creates on its own synchronized states that look like seizure activity in slices, and they self-terminate. And if you make the dynamics a little bit more complex, like in that case here, you have seen that probably that there are transitions between wave-like patterns and low amplitude oscillations up to extreme events that can be observed in this system without change of any kind of control parameters. This is self-generated. The underlying structures are chaotic saddles with some channel-like structures in that case, something like a 20,000 dimensional space. This is just fantasy. That was just an idea of how can we describe that. If this is really true, I have no proof for that right now. Yeah. But that can be done. And if you use these concepts then also for some realistic data, you go here onto a topology that has been measured from the brain with some MRI technique, and you compare that with what can be observed in the real human EEG, the equivalence is striking. And this is something that has not been taken into account so far, namely the impact of the coupling topology. Yeah? Reduction to a lattice or reduction to a random network is not always helpful, particularly in that cases here. So, and then you can ask, of course, what is this? Is this disease not just something that is an altered dynamics of neurons or neuronal pools, or is there also some kind of a alteration in the coupling topology and in the wiring of these networks, something that can be observed maybe later with an improvement of different imaging techniques. At the moment, we do not have access to this because this resolution is much too coarse in that sense. So I'm done. Some conclusions. I hope I could convince you that this brain is an adaptive, plastic, open, nonlinear network dynamical system that is designed to learn, and this is the problem that we are faced with if we try to understand epilepsy and also to treat epilepsy, because whatever we are doing, we will perturb the system. A system that is designed to learn, so it will also learn the perturbations. Think about that, what would be the consequence of that? No? The epilepsy is a disorder of large-scale neural networks. I mean, what you find in the literature is that there are networks and networks and networks, and they collide with these networks and these networks. I'm not talking about a speech network and a language network and the visual system network. These are local networks. Yeah? In that case, this is really a large scale. And if I say large scale, then I mean it extends over both hemispheres. This is basically the whole brain that is affected, although it looks local. Yeah? Always use the wrong one. Sorry for that. This recurrent intermittent malfunction that pops up. This is not just a dynamical effect, but it could also be, as I said before, some kind of an effect that comes from the coupling, an altered coupling. You need to take into account that alterations in the coupling is something that is also modified by aging. Yeah? And this is also what we see if we look at the distribution of epilepsies over age. It is mostly some kind of U-shaped like distribution. Younger ages, then it settles down. This is this 1%. And then with increasing age and with the observability of higher ages, because we have a growing aging population, we see more of these cases again. So there is also some kind of an indication that there might be also some kind of an aging effect that is behind this phenomenon. The critical transitions that we have here in these cases, they are detectable. Why this is not always the case? This still needs to be figured out. We have not yet an understanding of what kind of transition that is. There are lots of new models, lots of new ways that have been developed in order to understand that. But up to now, this is insufficient. The time series analysis techniques that we have, it looks like, particularly if we go into the direction of measuring interactions, that there is an end. We have almost everything. Any kind of in dynamical systems, in terms of interacting stochastical systems, anything that is available from the conceptual side has been translated into an analysis concept. So, if this does not work, what does this mean? We have no idea right now what this actually means. This is probably too complicated, this whole process, and then we should not touch upon that, but of course not. So, and then if we want to control that, this is then the big question of how to do that. At the moment, all these control techniques are made for basically for a static system where there is no kind of dynamics, there is no kind of adaptability. And if you do control in an adaptive dynamical system, I think even in mathematics, there is not yet a fully developed theory to really understand what is going on there. And with that, I thank you for your attention.
Thanks a lot. Times for questions. Yeah.
Thanks for the lecture. There is a slide in the start with intracranial EEG with a seizure. In that slide, there is a start in some channels from the seizure.
Yeah.
And at some time, you see a synchronization in another area. The synchronization collapses, and after you have a new synchronization. Yes, I think it's this one. Yes. So that there is the being.
How do you define synchronization?
I mean, I'm assuming that you can see a possible seizure in the channel.
No,
yes.
what you describe is that there is a similar time course. Is this synchronization?
Yeah, well, maybe not.
Yeah, this is exactly this uncertainty that I'm criticizing.
Yes.
Yeah? I know that you come from that field.
Yes.
Yeah? So you describe something, you look at something that oscillates, and then there's something that oscillates.
Yes.
Are you sure that there is a synchronization mechanism behind that?
No.
What is this? Yeah? Is this by chance? Is this really an active mechanism that leads to this effect? Or is this something that is, because we have macro electrodes, we measure something that is extremely local, we see that there is some kind of an oscillatory motion, and in another area there's also an oscillatory motion. Why?
Yes. So, for example, I cannot assume that the last part, we cannot assume that's a synchronization either.
Yeah.
Oh, okay.
Make sure that it's like that.
Well, but even if you don't get synchronization as a result of like two different brain regions, if you get something as a spike, it means many neurons are firing at the same time, because you wouldn't get the firing of a single neuron.
Yeah.
So at least locally, you would get some synchronization.
Yeah. Locally.
Okay.
But not globally.
It makes sense.
Again, looking locally, what would expect first that neurons to have a local synchronization after you do not see anything, and in the end you see a new local synchronization? There is any mechanism, maybe a homoclinic bifurcation or anything like this that explains that?
Could be. You see, we don't know it. Yeah. If you have on the local scale what he described, you have a local synchronization of a bunch of neurons. If in order to produce a spike, you need something like 0.6 square centimeter, something like 20,000 neurons that would need to fire really in synchrony. Then you will see the spike in that data. Otherwise not. What does this mean? If you have something that is local, and then you go a little bit far away, and you have then a wave phenomenon. What is this? Is this now a stupid superposition phenomenon? There are methods that had been tested already in the 80s where people did exactly that. Yeah? You try to simulate the brain simulate the brain, a small tissue of brain, and then you extend it to some large structure, and on average, you find 0. If you don't take into account the topology here. So there is some kind of an emergent phenomenon that goes from the microscopic level of neurons to the less or more mesoscopic level, if you want to call it like that, where you have a network, and if you then extend into a much higher spatial scales, yeah, another kind of emergence happens. What are these transitions? Transitions not in time, but also in space. The concepts that we have for that come all from observations that you think you treat this neuron as an oscillator. Makes sense, yeah? But it's not a size effect. It is probably a scaling effect. It is probably not even converging. It's not known so far.
So I'm not from the field, so maybe what I'm going to say is very stupid, but my take-home message is that somehow there is some missing theoretical framework to understand these things.
Yeah.
At the end, there was a little bit of an effort to introduce that framework based on these integrating fire and coupled neurons. So my question is, how is this connection between the attempts to build this framework and the data? How are you validating that? Like, for example, I'm really interested in distribution of inter-event time distributions. So maybe I'm biased towards testing with that, but I'm curious to know whether there is any attempt to...
Yeah. So building a relationship is, at the moment, heuristically. Yeah, if you say, I have some observation on the EEG, and I do some kind of a time series analysis with that, and I see these and these and these changes, can I find something similar in some adequate model? Up to that point. Yeah. The point is now, if you have models, you can probably treat them analytically. From what we have from the data, this is mostly numerics. And building a bridge between these two worlds, so far, I think that is not yet available. Yeah, I think people working on that, but I would not claim that there is already some kind of a solution to that. Yeah. Yes. Yeah. We need to have some kind of a testable way to do that. Yeah. Testable means, and this is the risk that we are doing here. Testable means we are doing perturbations. Yeah? And in this system, this is risky. Yeah? So, and if you rely on events, I mean, whatever you define as an event, be it a spike, an spike interval or whatever, there are lots of patients that do not even show up with spikes. Or these phenomena are so rare that you would need really long observation times in order to say anything about distributions. And if you think in terms of where does it happen, this is not a local effect. Spikes happen everywhere in the brain. Yeah? It could be, if you interpret that now from the side of a network, this is something that is being generated everywhere. Yeah? But if you have some kind of an highly diffuse phenomenon, how to trace that then back into the concept of what you have before? Okay? No. Yes, it is disappointing. Yes, but no, but this is just a warning to go into some field where you say, we know for 3,000 years that this disease exists, and now we come with the hottest shit that has been developed in the natural sciences, and then we solve this. Yeah, no, yeah. This is the risk that we run into. Yeah? And then you see the frustration that you observe every 25 years. Yeah? Then you run into this Kuhn cycle, and then you say, okay. And then you need to start again. I mean, we are now close to something where we have control schemes. Yeah? If you go back to the early 70s, there was nothing in that direction. There were just dreams on that. Now we have already some systems, and we have already now the next generation of these systems where you can do something. Yeah? But it's just a warning that the system is much too complicated to go from a simple and I'll put it a little bit nasty, a simple engineering system to such a complicated system. Yeah? Particularly the adaptivity. This is the risky point here. It was,
So I had a different kind of question. Is this randomly distributed among the population, or is there some genetic component, or are there some personality traits associated with epilepsy that you can say, for example, some sleep disorder or something else that's associated with epilepsy?
you can observe any other comorbidities that you want.
But is there a correlation between having epilepsy and, for example, male, female, or
I would not call it correlation,
genetic
I would call it
components?
association. I would not even call it a correlation, it's an association. From
people don't
association
know?
studies, you observe it here and you observe it there.
No, but is
That's
it randomly distributed? Does somebody have a random percentage of getting this? Or is it, for example, if his father has it, does he have more chance of getting it? I'm just asking, it's not
If
known?
you if you think that there is some kind of a genetic origin, I don't know the amount of or the contribution of genetically based epilepsies is something in the order of a per mil range.
I see. So some types of epilepsy might be genetic.
Yeah.
Okay.
There are
Thank-
certain mutations and genetic predispositions. So in some families you do see it. But
another one.
essentially, so
No, go ahead.
essentially, every human being has a threshold for a seizure. Now, a seizure is not the same as epilepsy, but every human being could be provoked to have a seizure.
Threshold for seizures.
Yes.
Something else.
Yes.
You can seize. 3 weeks of mathematics, no sleep, no alcohol as much as possible, you will seize. Yeah? But this is not epilepsy.
Yeah.
Yes.
Klaus, if I could, Klaus, if I could ask a question. In your this was a lovely presentation. Thank you very much for summarizing all of this. You know, as you say, every time there's a new development in analysis, it comes into our field.
Yeah.
Any thoughts on machine learning, AI, and where
I
they go?
mentioned machine learning already that I don't like that. Okay. Matilda is
Yeah.
first. Yeah.
And
We do this later.
I'm trying to translate. I enjoy your talk very much. What I'm trying to translate your message is, are you telling us that the thing is so difficult that maybe we don't know if you're going to solve it like that? Or would you tell us just be bold and go where no man has gone
Be
before?
cautious.
So,
Be cautious.
be cautious.
Yes.
And bold or not bold?
Have you read Salman Rushdie?
Sorry?
Salman Rushdie's books? Have you read that? If IFF, if and only if, made a statement, it's a process probably too complicated to explain with the current knowledge. I don't want to disturb current knowledge, and also not the increase, but I only say be cautious.
Okay, thanks.
More questions? Okay, if not, we can stop here, and thanks our speaker again.
Thank you.
Yes, good. You know, the